The paper discusses the problem of robust matrix completion, RMC, where a partially observed low-rank matrix is corrupted by sparse noise. The authors consider a non-convex method that alternates between a projected gradient step for the low-rank part and a thresholding step for the sparse noise part. They establish that this method can achieve linear convergence for a general class of thresholding functions, including soft thresholding and SCAD, using leave one out analysis. This is the first leave one out analysis on a non-convex method for RMC. The result also improves the sampling complexity of existing results for low-rank matrix completion. This research paper discusses the problem of robust matrix completion, RMC, with sparse outliers. The authors introduce three assumptions. 1. The ground truth matrix L star operator is mu incoherent, meaning that its singular vectors are not too sparse. 2. Each entry is independently observed with probability p. And 3. Each observed entry is independently corrupted by an outlier with probability alpha. These assumptions are standard in the matrix completion literature and can be considered as separation conditions on L star operator, S star operator. The authors then introduce notations and definitions, including the compact SVD of L star operator, the condition number kappa, and the spectral and Frobenius norms of a matrix. They also define the projection operator p omega, which projects a matrix onto the set indexed by omega. The paper then discusses the non-convex RMC algorithm with general thresholding functions. The algorithm combines the SVP algorithm for low-rank matrix completion with a thresholding function to handle sparse outliers. The authors consider a general class of thresholding functions that satisfy three properties. 1. The function is 0 for inputs less than or equal to a parameter lambda. 2. The function is Lipschitz continuous. And 3. The function has a bounded difference with the identity function. The authors propose a non-convex method, formally described in Algorithm 1, which uses a general thresholding function satisfying these properties. They provide a theoretical guarantee for this algorithm, which is applicable to any thresholding function satisfying the three properties. The guarantee is stated in terms of the spectral and Frobenius norms of the estimated matrix. The paper also presents phase transition tests, which suggest that both soft thresholding and SCAD functions work desirably. The authors justify this claim by showing that these functions satisfy the three properties. The non-convex method is then applied to the RRMC algorithm, which combines SVP with hard thresholding for outliers. The authors discuss the limitations of the leave one out analysis in 11, and the difficulties in extending it to RRMC. The paper presents a novel approach to robust matrix completion, focusing on the recovery of low-rank matrices from corrupted and incomplete data. The authors introduce two algorithms, RMCSOFT and RMCSCAD, which leverage non-convex optimization techniques to efficiently solve the problem. These methods are compared with existing approaches, such as RPCAGD and RRMC, through extensive numerical experiments. The authors first provide an empirical phase transition comparison for RMCSOFT and RMCSCAD, demonstrating their effectiveness in various scenarios. They then outline the key steps of their proposed algorithm, which involves an initialization step followed by a series of iterations that progressively refine the estimate of the low-rank matrix. The algorithm utilizes a thresholding function to eliminate outliers and noise from the data. The paper also includes a detailed theoretical analysis of the algorithm's performance, providing conditions under which the proposed method can successfully recover the underlying low-rank matrix. Specifically, the authors establish that if certain assumptions are met, including a sufficient number of samples and a suitable choice of parameters, the algorithm will converge to the correct solution with high probability. Numerical experiments are conducted to compare the performance of RMCSOFT, RMCSCAD, RPCAGD, and RRMC across different problem settings. These tests demonstrate that the proposed algorithms outperform existing methods in terms of both accuracy and computational efficiency, particularly when dealing with high-dimensional data and large outlier probabilities. Overall, this paper contributes significantly to the field of robust matrix completion by introducing novel algorithms and providing a comprehensive analysis of their performance. The proposed methods offer promising solutions for real-world applications involving large-scale, noisy, and incomplete datasets. The proposed algorithm, RMCSOFT, exhibits superior performance compared to RPCAGD in phase transition results, as shown in Fig. 2. The algorithm's update rule for the low-rank matrix lieutenant can be written as LT plus 1 equals PR, L star operator P1 P omega, street S star operator, plus H omega, lieutenant L star operator, where H omega equals I1, PP omega. To establish convergence, auxiliary leave one out sequences are introduced, which decouple the statistical dependence between the rows and columns of the matrix. The update rule for the low-rank part can be written as LT plus 1, I equals PR, L star operator at, I1 plus at, I2, where at, I1 and at, I2 are defined in terms of the perturbation matrix E. The deviation between the estimated low-rank matrix LT plus 1, I and the ground truth L star operator can be measured by the orthogonal Procrustes problem, which yields an optimal rotation matrix GT plus 1, I. The error bound for LT plus 1, IL star operator can be established using lemma 1, which states that if the perturbation matrix E is small enough, the error bound can be controlled by the deviation between the singular value decompositions, SVDs, of LT plus 1, I and L star operator. Furthermore, the entry-wise error for the outlier estimation can be controlled using lemma 2, which states that if the error bound for LT plus 1, IL star operator is small enough, the support of the estimated outlier matrix street I is contained in the support of the ground truth outlier matrix S star operator. The proof of these lemmas relies on establishing proximity between different sequences, which is achieved by bounding the deviation between the SVDs of LT plus 1, I and LT plus 1, M. The algorithm's performance is evaluated using experiments, where the percentage of successful recoveries among 20 independent trials is recorded. The results show that RMCSOFT, RMCSCAD, and RRMC exhibit similar performance, which is superior to RPCAGD. The phase transition results are presented in Fig. 2, which shows the percentage of successful recoveries as a function of the rank and the number of outliers. Theorem 2 establishes that under the assumptions of Theorem 1, for iteration 1 is less than or equal to t is less than or equal to t, where t equals no, 1, several inequalities hold with high probability. These inequalities include bounds for max 0 is less than or equal to I is less than or equal to 2n, vextend double at 1, I, vextend double 2, max 0 is less than or equal to I is less than or equal to 2n, vextend double increment t, I, vextend double 2, infinity, and max 0 is less than or equal to I. M is less than or equal to 2n, vextend double dt, I, m, vextend double f. These bounds are essential for the proof of Theorem 1, which can be preceded as follows. First, consider the case t equals 0. Since vextend double L0L, vextend double infinity equals barred BL infinity is less than or equal to micro Rn sigma 1, by lemma 2, sup, S0, subset equal omega S, vextend double P omega, S0S, vextend double infinity is less than or equal to C thresh micro Rn sigma 1. For the case t is greater than or equal to 1, due to 3a, lemma 1 is applicable. Thus, we have vextend double lieutenant L, vextend double infinity is less than or equal to barred BL increment t, barred BL2, infinity, barred BL fort, barred BL2, infinity plus, barred BLF, barred BL2, infinity, barred BL sigma t, barred BL2 plus 3 plus 4 kappa, barred BLF, barred BL2, infinity, barred BL at 1, barred BL2. This leads to a bound involving micro r, n, sigma, and gamma t. In the following sections, the induction hypotheses for t equals 1 and t greater than 1 are verified. The key differences between our proofs and the ones in 11 are also discussed at the beginning of each section. In the base case, our proofs and the ones in 11 are mainly different in two aspects. We use lemma 4 instead of 11, lemma 21, to bound barred BLH omega L barred BL2, and use Bernstein's inequality applied to vectors instead of scalars to bound vextend double et mh I omega L v1 m vextend double 2, both yielding better bounds. Next, let us establish 3a, 3c for t equals 1. For all I element of 0, 1, 2n vextend double L0 IL vextend double infinity equals barred BLL barred BL infinity is less than or equal to micro Rn sigma 1. It follows from lemma 2 that sup S0 I subset equal omega I intersection omega s vextend double p I omega S0 is vextend double infinity is less than or equal to c thresh micro Rn sigma 1. Step 1. The bound for vextend double E0 infinity vextend double 2. First consider vextend double E0 I1 vextend double 2. Recall from remark 1 that with high probability, p omega s is 2 alpha p sparse. Conditioning on this event, one has vextend double E0 I1 vextend double 2 equals vextend double p1p I omega s0 is vextend double 2 is less than or equal to p1 2 alpha pn c thresh micro Rn sigma 1 is less than or equal to gamma 2 c01 kappa 2 micro R sigma R, where the first inequality follows from applying lemma 3 to the 2 alpha p sparse matrix P I omega S0 is, and the second inequality holds if alpha is less than or equal to 1/4 CO1 kappa 3 micro R2 gamma c thresh. For vextend double E0 I2 vextend double 2, one has vextend double E0 I2 vextend double 2 equals vextend double H I omega L vextend double 2 is less than or equal to barred BLH omega L barred BL2 is less than or equal to C4 log n p barred BLL barred BL infinity plus radical log n p radical barred BLL barred BL2 infinity plus vextend double L T vextend double 2 infinity is less than or equal to C4 log n p micro Rn sigma 1 plus radical log n p radical micro Rn sigma 1 is less than or equal to 2C4 radical micro R log n p sigma 1 is less than or equal to gamma 2C01 kappa 2 micro R sigma R, where in these inequalities we use lemma 4 which holds with high probability for some universal constant C4 greater than 1, and the last inequality holds if p is greater than or equal to 16 C42 C20 gamma 2 kappa 6 micro 3 R3 log n n. Therefore, vextend double E0 I vextend double 2 is less than or equal to vextend double E0 I1 vextend double vextend double 2 plus, vextend double, vextend double, vextend double E0. I2, vextend double, vextend double, vextend double 2 is less than or equal to 1C01, kappa 2 micro r sigma r gamma. The paper discusses the bound for the matrix increment 1, infinity, which is a key component in the analysis of the matrix perturbation. The authors start by splitting the matrix into two parts, one of which can be bounded using the property of the matrix V1, M. They then utilize the property of the random variables on the mth row and define a new variable, Vk, to bound the norm of the matrix. By applying lemma 10, they obtain a bound for the matrix norm, which involves the norm of L star operator and the norm of V1, M. Next, the authors bound the matrix norm of EdMe0, IV1, IV1, MG1, I, M, splitting it into two parts and bounding each part separately. The first part is bounded using the property of the matrix norm and the bound in equation, 4. The second part is bounded using the bound in equation, 5, and the property of the matrix norm. Combining these bounds, they obtain a bound for the matrix norm of EdMe0, IV1, IV1, MG1, I, M. The authors then combine the bounds for T1 to T4 to obtain a bound for the matrix norm of increment 1, infinity. This bound involves the norms of L star operator, V1, M, and D1, infinity, as well as the parameters C0, C10, C4, gamma, and kappa. Finally, the authors bound the matrix norm of D1, infinity, which is done by splitting it into two parts and bounding each part separately. They use Weyls inequality and the bound of EO, M to bound the first part, and then apply lemma 8 to bound the second part. This results in a bound for the matrix norm of D1, infinity, which involves the norms of W0, M, V1, M, and F1, M, as well as the parameters delta and sigma star operator. In the context of quantum computing, this paper discusses the concept of quantum error correction and its implications for achieving fault-tolerant quantum computation. The authors introduce a new quantum error correction code that can be used to protect quantum information against errors due to decoherence and other quantum noise. This code is based on a combination of classical error correction techniques with quantum error correction methods, allowing for the protection of both classical and quantum information in a single code. The paper begins by discussing the importance of fault-tolerant quantum computation and the challenges associated with achieving it. It then reviews existing quantum error correction codes, including surface codes and stabilizer codes, before introducing the new code proposed by the authors. This new code is designed to offer improved error correction capabilities compared to existing codes, particularly in terms of its ability to correct errors due to decoherence and other quantum noise. The authors provide a detailed analysis of the properties and performance of their new code, including its error correction capabilities and resource requirements. They also compare the performance of their code with that of existing quantum error correction codes, demonstrating its potential advantages in certain scenarios. Finally, the paper concludes by discussing the implications of this new code for achieving fault-tolerant quantum computation and the potential applications of such a code in quantum computing systems. Overall, this paper contributes to the ongoing research efforts aimed at developing robust and efficient quantum error correction methods that can help to overcome the challenges associated with quantum noise and decoherence. The proof of the bound for increment t plus 1, I infinity, 2, infinity is presented, which is a crucial step in establishing the convergence rate of the proposed algorithm. The bound is derived by splitting the estimation into four terms, T1, T2, T3, and T4, and then bounding each term separately. The bounds for the first three terms are obtained similarly as in the base case, resulting in a bound of 16C0, 1, kappa micro r, gamma t plus 1. To bound T4, the case where 0 is less than or equal to I is less than or equal to n, 1 is less than or equal to m is less than or equal to n, and I does not equal m is considered. The bound for ETMET, IVT plus 1, I2 is derived, which involves bounding ETMET, I2VT plus 1, I. This is technically involved, and the proof is divided into three parts: bounding T1, T2, and T3. Bounding T1 involves applying lemma 10 to get a bound of C10, square root n log n p plus square root log n p lt ml star operator infinity sign vt plus 1 m2 infinity. This bound is further simplified to C10 C0 sigma star operator r kappa micro r gamma t plus 1 square root micro r n plus increment t plus 1 infinity 2 infinity, provided that p is greater than or equal to 576 C210 gamma 2 kappa 2 micro 2 r2 log n n. Bounding T2 involves expressing LT, MLT, I as the sum of 4 terms, and then bounding each term separately. The bound for T2 is derived as ETMH, I, omega, dt, m, IU sigma t, m, vt, m, t, vt plus 1, m2, which is further simplified to C10 C0, sigma star operator r, kappa micro r, gamma t plus 1, square root, micro r, n, plus increment t plus 1, infinity 2, infinity. The bounds for T1 and T2 are crucial in establishing the convergence rate of the proposed algorithm. The proof is highly technical, and the bounds are derived using various lemmas and inequalities. The final bound for increment t plus 1, I infinity, 2, infinity is obtained by combining the bounds for the 4 terms, T1, T2, T3, and T4. Here is a combined summary of pages 19 and 20 of the research paper. The authors apply lemma 11 to derive an upper bound for T2a, which involves the terms dt, m, I, ut, I, sigma t, m, and vt plus 1, m. They then utilize lemma 10 to obtain a further bound, resulting in an expression involving logarithmic terms and the maximum eigenvalues of vt, m and vt plus 1, m. By applying lemmas 10 and 11, they establish an upper bound for r, m, in terms of logarithmic functions and the eigenvalues of vt, m and vt plus 1, m. The authors then proceed to bound T2b, which is similar to T2a, by replacing dt, m, iu sigma t, m with ut, east, m, I. They apply lemma 9 to obtain an upper bound for Saint, m, I, which involves the terms Hadwider L star operator, Hadwider a-1, m, and tilde a. This leads to a bound for T2b in terms of logarithmic functions and the eigenvalues of vt, m and vt plus 1, m. For T2c, the authors apply lemma 12 to obtain an upper bound, which involves the terms h omega, ut, I sigma t, I, dt, I, mv, and vt plus 1, m. They then utilize the bounds for T2a and T2b to establish an upper bound for T2c in terms of logarithmic functions and the eigenvalues of vt, m and vt plus 1, m. Finally, the authors bound T3, which involves the terms etmet, I, vt plus 1, I, vt plus 1, m, gt plus 1, m, and gt plus 1, I. By applying lemma 5, they establish an upper bound for T3 in terms of logarithmic functions and the eigenvalues of vt, m and vt plus 1, m. The authors assume that P satisfies certain conditions to ensure the validity of these bounds. The paper provides technical proofs for bounding various terms in a machine learning model. On page 21, the authors derive bounds for the terms $wide tilde, t underscore $1 to $wide tilde, t underscore $3, which are used to establish the convergence rate of the model. The bounds are obtained by applying various inequalities and using the properties of the model's parameters. The authors first bound the term $wide tilde, t underscore $1 by using the inequality $wide tilde, e underscore m, I, v underscore t plus 1, I, wide tilde, e underscore m, I, v underscore t plus 1, m underscore 2, lect 3 plus 2 c underscore 10, c underscore 0, sigma underscore r caret, kappa, mu underscore r, caret, 1/2, gamma underscore t caret, 1/2, plus 3 plus 74 c underscore 10, c underscore 0, delta underscore t plus 1, infty, dollar. They then combine this bound with the bounds for $wide tilde, t underscore $2 and $wide tilde, $3 to obtain a final bound for $wide tilde T underscore M I V underscore T plus 1 I V caret underscore $2. On page 22, the authors focus on bounding the term delta underscore T plus 1 0 M $. They use the inequality delta underscore T plus 1 0 M lec 2 sigma underscore R caret W underscore T M F underscore T plus 1 M W underscore T M F underscore T plus 1 M caret underscore F $, and then derive bounds for the terms $B underscore $1 to $B underscore $4. To bound $B underscore $1, the authors use a technique inspired by 9, where they consider an equivalent model that generates omega underscore S caret $. They show that P caret M omega S underscore TS underscore T caret V underscore T plus 1 M underscore F $, can be bounded using lemma 13. They also derive a bound for U underscore T plus 1 M G underscore T plus 1 M caret T sigma underscore T plus 1 M caret 1/2 U caret sigma caret 1/2 underscore 2 INFTY $. The authors use these bounds to establish the convergence rate of the model and provide a final bound for delta underscore T plus 1 INFTY $. The results are obtained under certain assumptions on the model's parameters, such as $C underscore 0 GEQ 6 C underscore 10 C underscore 13 $. Overall, the paper provides a technical analysis of the machine learning model, deriving bounds for various terms and establishing the convergence rate of the model. The results are obtained using a range of mathematical techniques, including inequalities and probabilistic arguments. The paper discusses the optimization of quantum algorithms, specifically focusing on the problem of minimizing the expectation value of a given Hamiltonian. The authors introduce a new algorithm, Quantum Approximate Optimization Algorithm, QAOA, which uses variational parameters to optimize the expectation value. They also provide a detailed analysis of the algorithm's performance and its relationship to the quantum phase estimation, QPE, algorithm. The authors start by defining the QAOA algorithm and its parameters, including the number of qubits, the depth of the circuit, and the variational parameters. They then provide a detailed analysis of the algorithm's performance, showing that it can achieve a high success probability in minimizing the expectation value of the Hamiltonian. The authors also compare the QAOA algorithm with the QPE algorithm, showing that QAOA can achieve better performance in certain cases. They discuss the limitations of both algorithms and provide suggestions for future improvements. In the second part of the paper, the authors focus on the analysis of the QAOA algorithm's performance. They provide a detailed bound on the error of the algorithm, which depends on various factors such as the number of qubits, the depth of the circuit, and the variational parameters. They also discuss the implications of this bound and how it can be used to improve the algorithm's performance. The authors also provide a detailed analysis of the algorithm's convergence properties, showing that the algorithm converges to the optimal solution under certain conditions. They discuss the role of the variational parameters in the convergence process and provide suggestions for optimizing these parameters. Finally, the authors discuss the potential applications of the QAOA algorithm in various fields, including chemistry, materials science, and machine learning. They also provide a detailed comparison with other quantum algorithms and discuss the challenges and limitations of implementing these algorithms in practice. Overall, the paper provides a comprehensive analysis of the QAOA algorithm and its performance, as well as its relationship to other quantum algorithms. It also discusses the potential applications and limitations of these algorithms, providing valuable insights for researchers and practitioners in the field of quantum computing. Theoretical recovery guarantees for the non-convex alternating projection method in robust matrix completion have been established through leave one out analysis, eliminating the need for projection and sample splitting. The method's performance is ensured by the choice of parameters, including the thresholding function, which must satisfy specific conditions. The conditions involve the constants C10, C0, and C13, as well as the parameters p and alpha, which must fall within certain ranges to guarantee the induction hypothesis. These ranges depend on the problem's dimensions, the rank of the matrix, and the noise level. The analysis provides a bound on the error of the recovered matrix, which is a function of the problem's parameters and the constants. The bound is given by the equation on page 27, which involves the maximum of two terms, each depending on the problem's parameters and the constants. The constants C10 and C0 must be chosen such that the conditions in equation 21 are satisfied, ensuring the induction hypothesis holds. The paper concludes by discussing potential future work, including accelerating the projection onto the low-rank part via Riemannian optimization and extending the analysis to robust completion of Hankel matrices and tensors. The references provided on pages 27 and 28 include works on matrix completion, robust principal component analysis, and related topics, highlighting the connections between these areas of research. The equations and conditions presented in the paper provide a rigorous framework for understanding the performance of the non-convex alternating projection method in robust matrix completion. The analysis relies on a combination of mathematical techniques, including leave-one-out analysis and the use of specific thresholding functions. The results contribute to the understanding of robust matrix completion and provide a foundation for future research in this area. The tables of references on pages 27 and 28 list works by various authors, including E. Abbey, J. Fan, K. Wang, and Y. Zhang, as well as H. Kai, J. F. Kai, and K. Wei, among others. These references cover topics such as matrix completion, robust principal component analysis, and related areas, demonstrating the connections between these fields of research. Here is a combined summary of pages 29 and 30 of the research paper. The paper presents a collection of useful lemmas and supplementary proofs, which are used throughout the manuscript. These results are mostly from the literature, and proofs for the new ones are provided. Lemma 3 states that if a matrix S is alpha sparse, then its spectral norm is bounded by alpha n times its infinity norm. Lemma 4 provides a bound on the spectral norm of a matrix H omega, Z, in terms of the infinity norm of Z and its maximum singular value. Lemma 5 gives a bound on the spectral norm of H omega, A, for any matrix A with rank at most K, assuming P is greater than or equal to log n. This lemma is used to establish the convergence of the proposed algorithm. The paper then defines several matrices, including L equals L plus E, F, and F, which are used to establish the convergence of the algorithm. Lemmas 6 and 7 provide bounds on the differences between F and Fg, and sigma G and G sigma, respectively, assuming that the spectral norm of E is sufficiently small. The paper also defines matrices A and A, which are symmetric and have topper eigendecompositions F lambda Ft and alpha lambda, F, T, respectively. Lemmas 8 and 9 provide bounds on the differences between F and F, and lambda G and Ga lambda, respectively, assuming that the spectral norm of W is sufficiently small. These lemmas are crucial in establishing the convergence of the proposed algorithm and providing bounds on the errors involved. They are used to analyze the performance of the algorithm and provide guarantees on its convergence. The presented proofs and lemmas establish a theoretical framework for understanding the behavior of certain matrix functions and their properties. The first proof demonstrates that the difference between two matrices, G and H, can be bounded by the product of the difference between their corresponding matrices, F, and the norm of the matrix W. This is achieved through a series of inequalities, including the use of the Davis-Cohn theorem. The Bernstein inequality, stated in lemma 10, provides a bound on the sum of independent random matrices. This inequality is used to establish a user-friendly version of the Bernstein inequality, which is essential for the analysis of matrix functions. Lemmas 11 and 12 introduce deterministic bounds on the norms of certain matrix functions. Lemma 11 establishes a bound on the norm of the matrix function H omega, apt, C, while lemma 12 provides a bound on the inner product of two matrix functions. Lemma 13 presents a high probability bound on the norm of a matrix function, specifically the matrix H omega, xyt. This bound is established under certain conditions on the matrix X and Y, and it is shown to hold simultaneously for all X, Y, obeying certain conditions. Finally, lemma 14 introduces the soft thresholding function and the SCAD function, which are used to establish three properties, p.1 p3. These properties are essential for the analysis of matrix functions, and they are used to demonstrate the behavior of these functions under certain conditions. The presented results provide a solid theoretical foundation for understanding the behavior of matrix functions and their properties. They establish bounds on the norms and inner products of these functions, which are essential for the analysis of various matrix functions. The results also demonstrate the importance of the Bernstein inequality and the Davis-Cahan theorem in establishing these bounds. Key equations and concepts. Vextend double lambda g minus g, tilde lambda. Vextend double f is less than or equal to bard bl lambda, bard bl2 plus. Vextend double, tilde lambda. Vextend double 2, bard blg minus h, bard blf plus. Vextend double h, tilde lambda minus g, tilde lambda. Vextend double f. Bard blg minus h, bard blf equals. Vextend double a, parent left big I minus, tilde sigma, parent right big bt. Vextend double f. Vextend double m. Summation display L equals 1 megaliter. Vextend double is less than or equal to C10, parent left big, radical big A sigma 2 log. D1 plus D2, plus a blog. D1 plus D2, parent right big. Vextend double ETMH omega, parent left big apt, parent right big C. Vextend double 2 is less than or equal to. Vextend double ET ma. Vextend double 2, vextend double R, M. Vextend double 2. Vextend double H omega, parent left big apt, parent right big C. Vextend double f is less than or equal to bard BLA, bard BLF max M. Vextend double R, M. Vextend double 2. The authors present a proof for lemmas 1 and 2, which are crucial in establishing the theoretical guarantees of the SCAD, smoothly clipped absolute deviation, penalty function in the context of low-rank matrix estimation. Firstly, the authors define the SCAD function, Tscad lambda, a, x, which is a piecewise linear function with knots at plus or minus lambda, plus or minus 2 lambda, and plus or minus a lambda. They then proceed to show that this function satisfies certain properties, such as being Lipschitz continuous with a Lipschitz constant of a 1, a2, and having a bounded difference with the identity function. Next, the authors provide a proof for lemma 1, which involves bounding the spectral norm of the difference between two matrices, L and L star operator. This is achieved by decomposing the difference into four terms, R1, R2, R3, and R4, and bounding each term separately. The bounds are derived using various matrix norms and inequalities, including the Frobenius norm, the spectral norm, and the 2 norm. The proof for lemma 2 is then presented, which involves bounding the magnitude of the entries of the matrix MLT, I, where LT, I is a truncated version of the matrix L. The authors use the properties of the thresholding function T and the definition of the SCAD function to establish the desired bound. Throughout the proofs, the authors rely on various lemmas and inequalities, including lemma 7, which provides a bound on the 2 norm of the difference between two matrices. They also use the augmented matrices, hat-wide L and hat-wider L star operator, which are constructed by appending the matrices L and L star operator with 0 rows and columns, respectively. Overall, the authors provide a rigorous and technical proof for lemmas 1 and 2, which are essential in establishing the theoretical guarantees of the SCAD penalty function in low-rank matrix estimation.